Hello, this is Mr. Henry, and welcome to Lesson 6.5. We are describing relationships from graphs. Okay. The central question says, how do I describe fundamental relationships from graphs? For those of you who've already done some stuff with scatter plots, which is another 8th grade content here, you will see a lot of similarity between this lesson and that lesson. We're basically talking like that line of best fit when you're talking about scatter plots. You're looking for, is it positive, is it negative, is it linear, is it nonlinear? Those sorts of things. Those same words are going to appear again in this lesson in almost the exact same context. Okay. Did you know that functions and relations sound confusing, but it's really just showing a relationship between two values. Like when we talk about a function, it's just the relationship. Usually, that relationship comes in the form of an equation. So an example like rainfall over time, or money made per year. That's a function. A plumber charges $36 an hour. You're comparing money and time. Hot dogs eaten per person, corn yield per acre. All of these relations can be graphed. They have an initial value. They have a rate of change. They're all linear functions. Well, could be linear functions, or hot dogs eaten per hour. That could be nonlinear if you slow down as you're eating your hot dogs over time. Okay. There is once again no new vocabulary. Yay! Let's get started. So we want to look at these graphs, and we want to basically describe the line, the function, in words, with as many descriptive words as we can. So when I'm looking at this guy, and I'm probably going to do more, we'll see if I do typing or writing. So this line here, this example A, things I can say about him immediately. I can say he is linear. I know because it is a straight line. Linear means straight line. I know it is positive. Or you could also say increasing. I know that because the line is going up from left to right. When you read a graph, you always read it from left to right, just like when you read a piece of paper. So if you imagine a little dude walking on the line, here he is, boom, boom. As this little guy is walking from left to right across your line, he's going up, 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 up. That is positive. That's a positive slope. If we found the slope of this line, it would be a positive number. You're going up and over, up and over. It's positive. You could also say it's increasing. If you're talking about money over time, it would sound weird to say that's positive. You'd say, oh yeah, your money is increasing over time. Okay? That's pretty much it. That's all I can really say about that line. It's linear. It's positive. Okay. Letter B. So that's my little dude over here. If my little dude starts walking along this graph here from left to right, he's always going, wait, let me draw. He always goes that way. So if he starts going that way, you see what's happening, right? He's going down. He's decreasing, or there's a negative slope. And is he going down at the same rate everywhere? I mean, right here, he's going down not too fast. But what happens as he keeps moving on? Whoa, whoa. The rate at which he's decreasing is not the same, because this is non-linear. It's not a straight line. It's curvy. And I don't know if you caught that. When I said the word rate, I said this line is not going down at the same rate, the same slope. The slope is changing. That means it's nonlinear. Over here, the first one, the slope stays the same. I didn't say the word rate here, but he's going up at the same rate everywhere because it is linear. Okay, so this guy is nonlinear and it's decreasing. Letter C. What in the heck is going on here? Well, it's got a couple things going on. First off, it's clearly nonlinear. My little dude, where are you, little dude? I need you. my little dude, he's going up, he's going down the slide. He's definitely non-linear, okay? It's not just going the same direction the entire time. It's non-linear. Now, as far as increasing or decreasing, what can we say? Well, it's kind of doing a bit of both. This one is both increasing and decreasing. Just kind of at different places. Like right here, he's increasing. Here, he's slowly decreasing. Here, he's decreasing very quickly. Okay? The rates are different at different places, as well as the slopes and the everything about it. Okay? So it's a little bit of everything. Letter D. I would like you, down here on your paper, pause the video and describe what is going on in letter D. Are you ready to continue? Hit play. We go through it together. Alright, so you should have found that letter D is nonlinear, and it is increasing everywhere. It has a positive slope. I should also put that in there. Everywhere. So this is kind of like American Ninja Warrior. So a guy like runs along the ground, and he has to run up the warped wall. Well, it's not flat. It's not just a ramp. He has to kind of go up and up and up and up, and it gets harder the higher you go up, because the wall's curving towards you. So this is non-linear, and it's increasing everywhere. Everywhere it's going up. Okay. 2 more. I would like you to pause the video, do letters E and F, describe what's going on, linear, nonlinear, positive, negative, increasing, decreasing. What do you got? When you're ready to continue, hit play, and we'll go through it together. Okay. So, letter E, we have nonlinear, because, well, it's not a straight line, I don't think, anywhere on here. And it's both increasing and decreasing. Because there's parts over here where he's going up, there's parts that are going down, parts you're going back up, so it's kind of a little bit different everywhere. Letter F. This one is linear. It's a straight line. The rate is the same everywhere. And as he goes across the graph, he is going down, 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 down. He is decreasing. Or you could also say it has a negative slope. Okay. So we call this a negative correlation back when we talk about scatter plots. Example 2. Describe the graph of a function. Now, this one, I mean, if you just looked at the whole thing, and I said describe the whole graph in one shot, you would say it's nonlinear, it's increasing and decreasing. But sometimes we want more information than that. Sometimes we want to, whoa, where's my little dude? There he is. Sometimes we want to break it down into different pieces. So, my little dude here in green, between days 0 and 1, between here and here, what's going on? Well, between those 2 points, it is decreasing. It is going down. Okay? Oh, and I remember there's something I wanted to change on this question. I want you to change right now. Because between days 0 and 1, the graph is not decreasing. That's not the thing that we're decreasing. And I think I have it changed on maybe your papers, but on here it's wrong. It's not the graph that's decreasing. It is the temperature. I want you to change that if it's not already changed. Because that's a very important distinction. We're not comparing days and graph. We're comparing days and temperature. And this is just bad wording on my part. Okay? So between days 0 and 1, the temperature is decreasing. The temperature is going down. Okay, the graph shows that change, but it's the temperature that's going down, not the graph. Between days 1 and 2, oh man, there we go. Between days 1 and 2, okay, my next block of time, the temperature is doing what? Well, from here to here, temperature is rising. It's increasing. You could say it has a positive slope. More likely because you're talking about temperature, you don't say, oh, the temperature's positive. People think it just means above 0. So usually we would say increasing. It makes more sense in the scenario given. But understand it does have a positive slope. Okay. Between days 2 and 4, the temperature is doing what? So between 2 and 4, the temperature is it's staying pretty much the same. It's like staying at this 30-degree thing. So if it's staying the same, we actually have a word for that. We're going to say that the temperature is constant. That's what constant means. Constant is math talk for something that stays the same. And it's not just math, even science. You say if something is constant, it's not changing. And then finally, in between days 4 and 5, the temperature is doing what? So day 4 to day 5, it decreases again. The temperature is decreasing. 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 Okay? So, important to note that between days 0 and 1, the temperature is decreasing. Between days 1 and 2, the temperature is increasing or increasing. Between days 2 to 4, the temperature is remaining constant, staying the same. And between days 4 and 5, it's decreasing again. So very quickly, on your paper, I want you to answer this question. So is the function represented by the graph linear or nonlinear? And explain your reasoning. So the one we just did a second ago, the one with the temperature. Is that linear or nonlinear? And why? Okay, so you should have answered by now. If you didn't, you can pause the video and give yourself a little bit more time. But I'm going to start talking about it. So obviously that graph was nonlinear. I said so at the beginning. I didn't realize this question was here. Because, I mean, look at it. It's nonlinear. There's parts of it that are going up. There's parts that are going down. It's not a straight line. There's parts that are straight, like between days 2 and day 4. I mean, it's a little curvy in there, but it's pretty much a straight line. That part, you could say, might be linear. But everywhere else, it's curvy. It's nonlinear. It's not the same everywhere. Okay? Example 3. Directions tell us to sketch a possible graph for each function. Tell whether the function is linear or nonlinear. Tell whether the function is increasing or decreasing. Okay, that seems simple enough. So James wants to buy some grapes from the store. Each pound of grapes costs the same amount. So we'd probably have like money and grapes. I can't write sideways. G-R-A-P-E-S. Grapes. Womp. Yeah. Alright, so he wants to buy grapes. Now, the part here that would help you figure out this out, first off, I think this line would cross right here. Because 0 grapes cost 0 money, right? Actually, would these variables be backwards? Yeah, I think they would be this way. Because the grapes would be the independent variable. The amount of money you spend would depend... Or this, yeah, this would be independent, this would be dependent. Yep, we're good this way. Alright, so each pound of grapes costs the same amount. That is actually the important sentence here. Each pound of grapes costs the same. The rate they charge you for grapes is the same. The slope is the same. So if your slope is the same everywhere, what would your line look like? Why, it would be linear, right? So if I start just from here, because again, 0 grapes cost $0. I start here, and I draw a straight line, as straight as I can. It doesn't really matter. Boom. Now, that's clearly linear. We said it was going to be linear. Now, would it be increasing or decreasing? I drew my line increasing. Is that right? Well, let's see. If you buy more grapes, does it cost more money? Yeah. Yes, it does. So this is positive, or you could also say increasing, because as you buy more grapes, it's going to cost more money. Okay? Letter B. Sam's company paints walls. The more people he puts on the job, the less time it takes. Show the amount of time for a job with X people. Okay? So, we need to show that the more people you add to a painting job, the less time it takes. So what would that look like? Well, would it go like, I'm brainstorming, so don't just copy this down because I might be wrong. I mean, does it look like this? If you add more people, does it take more time? Because these are both going up, so okay. So like, if more people are on the job, does the amount of time it takes to paint the wall go up? That's what this graph is showing. Now, that doesn't make much sense. Okay, so it's probably not positive. It's probably negative. Okay, so now the amount of time it takes to do a job goes down. Now, let me switch my variables. I don't like these variables. Just even for like understanding what's going on in the problem. This makes more sense to me. For example, this. Okay, we add more people to the job. So now we have 1 person, 2 people, 3 people, 4 people, 5 people, 6, 7, 8. And it changes how long it takes to do the job, right? Because if you have 1 person, it's going to take a lot longer. If you had 2 people, less time. 3 people, even less. 4 people, less. More. And so you got 8 people, and it takes almost no time at all. So I think I like this decreasing. This makes sense in terms of the problem. Okay, so that is decreasing. Now, we were supposed to tell if it was linear or nonlinear. Well, the line I drew was linear. Do you think it'd always be like that, or do you think it'd be, I mean, as a possibility, more like this? Or like this? I mean, I'm just thinking, oopsie. I'm just thinking of different possible graphs. I don't know. I mean, it depends on how you think. I don't think this one would be very good because as you add from here, like 1 person to 2 people takes about the same amount of time, and 3 people takes the same amount of time, and then finally it just goes down very quickly. I don't think that one would work. Okay? So thinking about it, I don't think that one. Whoa, too much. Sorry, wrong one. What about this one? So 1 person, and like the more people you add, it only is slowly decreasing the time it takes. Like here it decreases a lot. So from 1 person to 2 person, it saves a lot of time. And then 3 people, it saves a little bit less. And 4 is less. And now, see how it's kind of getting like flat here? Which means if you would add 9 and 10 and 11 and 12 and 15 people, it's going to stay about the same amount of time. So I don't think that would make sense either. So I'm going to go ahead and say I like our linear graph. I think linear would work best here. So I'm going to say this is linear because each person you add would take off time of your job by, should be about the same amount as long as all the people are painting at the same speed. Okay. Same thing. So linear or nonlinear, increasing, decreasing, sketch your graph. So it says a car traveling at a constant speed consumes about 2 gallons of gas per hour. The car starts with 9 gallons of gas before it leaves for its trip. Okay, so I want you to make a sketch of that, a possible sketch of that, and then describe whether that function should be linear, nonlinear, increasing, decreasing. So it looks like it's talking about the amount of gas it takes for the car to run. Pause. When you're ready to continue, hit play, and we'll go through it together. Okay. So it says the car starts with 9 gallons of gas. 1, 2, 3, 4, 5, 6, 7, 8. There's my 9 gallons of gas. And then it says it uses about 2 gallons of gas per hour. So every hour it uses about 2 gallons of gas. So 1 hour, 2 gallons is gone. Another hour, 2 gallons is gone. Another hour, 2 gallons is gone. 2 gallons is gone. So I think my graph, if I draw a line through it, I think that represents what it's saying. A car traveling at a constant speed consumes about 2 gallons of gas per hour. 2 gallons, 1 hour. 2 gallons, 1 hour. The car starts with 9 gallons of gas before it leaves for its trip. And here, 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's 9 gallons of gas. So this is very clearly linear. They even tell me in the problem what the slope is. Gallons per hour. That is a rate. That is my slope. It tells me the rate is 2 gallons per hour. And then it even tells you what the y-intercept would be. This is decreasing because the amount of gas you have in a car goes down over time. You're burning it up as you're driving down the road. Okay, letter D. Each time a set of cells divide, it doubles. The number of cells, okay? So if there were 5 cells, after they divided, there would be 10, then 20, and 40, etc. Show the number of cells after X divisions. Okay, so divisions and cells. So like if I even take that example, now I can't really do it exactly here, but it says it doubles each time. So if you start out with, say, 5, after the first division, it says it goes up to 10. The second division, what did it say? 20. So if I'm kind of 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. After 2 divisions, it's up to 40. No. I'm not remembering right, am I? One division begins with 5. After divided, it would have 10. After 2 divisions, you double 10, which I can't apparently count because that's not 10. There we go. Starts with 5. 1 division, it has 10. 2 divisions, it has 20. The next division, it would have 40. And the next division, if I could do it, would have 80. So if I connect them, trying to make the line as smooth as possible, well, that is increasing. The number of cells is going up very quickly. Okay, so it's definitely increasing. See, it's going up. And this is nonlinear. It's not going up by the same amount each time. It went from 10 to 20 to 40 to 80, 160. It's increasing. The word is exponentially. It's increasing incredibly fast. This is non-linear. And I can actually graph the stuff they tell me to show that. All right. These two are both for you. So I want you to pause the video and do them on your own. When you're ready to continue and check your answers, hit play, and we'll go through it together. Letter E says, a factory starts off with 200 pounds of plastic used to make toy soldiers. To me, that it starts with 200 pounds is an initial value. So in my head, I'm imagining some equation. Starts off with 200 pounds, okay? Sketch the graph for the amount of plastic left after the factory made X soldiers. Okay, so let's think about it. If the factory's making these toy soldiers, and we're supposed to graph how much plastic they have left, would the amount of plastic be going up or going down as they're making soldiers? Well, it's probably going down, right? I mean, you're using these plastics to make the soldiers. The amount of plastic you have left is going down each soldier you make. So I need a negative slope. So I'm going to say right now, already, I know my graph is going to be decreasing, because the amount of plastic left after each toy is going down. And would this be linear or nonlinear? Well, let's think. Nonlinear can look like this. But that would make sense. Like if I make one soldier and then 2 soldiers and 3 soldiers and 4 soldiers, and this would be plastic left. Okay. Like, is one soldier going to take a whole ton of plastic and the next soldier take a little bit less and a little bit less and a little bit less? I don't think so. Each soldier should take the same amount of plastic if you're making them all the same. So to me, because you're making little toy soldiers, I think your slope here would be just some number. I think it would be, it'd be, well, linear is what I'm trying to get at. Because each soldier takes the same amount of plastic. So one soldier takes that much plastic. The next soldier takes the same amount. The next soldier takes the same amount, and the same amount, and the same amount. Each soldier takes a little bit more plastic. So I would say that this is linear. And it would start with 200 pounds of plastic. So that's what I would make my little sketch. Well, it'd be nice if I would label here, I guess. So each soldier uses plastic. This is the independent variable. Dependent variable. The amount of plastic you have left depends on the amount of soldiers you've made. Okay? And so I start with 200 pounds, and it decreases each time I make a soldier. I only have a little bit less plastic left to make more soldiers. Letter F. You have a bag with 100 Skittles in it. Okay? Again, in my head, I don't even know if this is linear or non-linear, but I'm just imagine I start with linear. I know that I'm starting with 100 Skittles. That sounds like my initial value. Your friends want to have some, so you evenly split your Skittles among X friends. Okay, so I'm taking this 100 Skittles, and I'm dividing it by however many friends I have. And there we go. So Skittles each with friends. So well, I can actually do this math pretty easily, because if I start out with 100 Skittles and if I have 0 friends, guess how many Skittles I get to eat? Yeah, that's right. I get to eat all 100 Skittles. Okay? If I have 1 friend and we split it evenly, how many Skittles do we each get? Well, we each get 50 Skittles. If I've got 2 friends and we each get, so there's 3 of us now, right? 3, because there's me and my 2 friends. So there's 3 of us all together. We would each get, well, 100 divided by 3 is 33. So 0, 10, 20, 30, 40. So 33.3 is like right about here. And then if I have 3 friends and me, that's 100 divided by 4 people is 25. So if there's 3 friends and me, we each get 25 Skittles. Now, I can keep going with this, but I can see what's happening. Look at it. This is decreasing. this is non-linear. I mean, 4 friends and me, which means 100 divided by 5 is 20. 5 friends and me, which is 100 divided by 6 is 16.6. 6 friends and me, which is 100 divided by 7. I don't know that. 14.2. So you see, like it's the amount it's going down has changed a lot. Here, it dropped a lot. When I added 1 friend, I lost half of my Skittles. And then when we added another friend, well, I didn't lose quite as many that time. And it gets less each time. So this is non-linear, and it's decreasing. Last example, multiple choice. Which graph below most likely shows the water usage at a house with X people living there? Okay, so go ahead and, well, think about it for a second. Get your answer, and don't just circle one. Why? Why did you pick the one you picked? You got to understand the thinking behind it. So do that. When you're ready to continue, hit play, and we'll go through it together. Okay, so hopefully you went through this, and there's one here you can very, very, very quickly cross off, and that would be this one. If you add more people, the amount of water you're using in a house is not going to go down, because you got more people using bathrooms and showers and brushing teeth and drinking water and cooking and all that kind of stuff. It's going to increase the amount of water you need. So this would not make sense that the more people you add, as the people go up, the water is going down. That doesn't make sense. Okay, so now you're down to B or C. Well, this one is linear. This one is non-linear. So let's see. I mean, here, the first bunch of people you add, it's kind of going up a little bit at a time. And then as you add more people, does it go up like much, much faster? And if I continue this line, it'll be going up and up and up, faster and faster and faster and faster and faster. Is that how it works? Think of it like a hotel. If a hotel has a couple guests, and they only use a little bit of water, and then they get like 10 guests, the amount of water goes up. And then they get like 100 guests. Does their water just like skyrocket? And then at 105, there's a ton more, and 110 even more and more? Or do you think more like this one? Each time they add one person, the amount of water that gets used goes up by about the same amount each time. Because this is a constant rate, meaning that each person uses about the same amount of water. This is non-linear, not constant. So each person uses much more, or uses more water than the person before them. Which one do you think makes more sense? Everybody uses the same amount of water, or each time you add another person, they use more water than the person before them? Because look, this person doesn't use a whole lot of water. The next person you add, it's a little bit more steep. The next person you add, it's even more steep and more steep. So this person right here, look at the slope of this. It's a lot bigger. Let me see what I can do here. So this slope of this person is more steep than the slope of that person. So they're using just a lot, their water using a lot faster. Now if you compare this person over here, look how much water that person used. That person used a ton of water. Do you think it makes sense that each person you add uses a lot more water than the person before them? Or do you think each person should use about the same amount of water? I would say this one. Okay? So that's what I would say letter B is probably more correct, and my reasoning, because each person probably uses the same amount of water, so that's a constant rate. And summary. It says, give at least 5 words you could use to describe functions. Okay. This has been lesson 6.5. Thank you for watching.